Here's the solution to one of each of the problems from the practice set. So you can see some sample solutions, and we will be going over the rest of this in class. So hopefully you'll have pretty complete solutions by then. As usual, the last page of this handout has answers on it if you want to look at the D2L version. All right, so the first set here are geometric series, but part of what I'm seeing some issues with is with notation, so I wanted you to think about what the notation would be in each of these cases. So let's look at number 3. I'd like to add the first 4 terms of this, but you can see that the index k starts with 2. So the first term will be what I get when I put 2 in for k. So that'll be 9 over 2 to the 4th. The next term will be what I get when I put 3 in. So that's 27 over 2 to the 6th. I guess there's no real reason for me to try to keep doing that. I know 3 to the 4th is 81, and the denominator I'll have 2 to the 8th, which is 256. And then finally I'll have 3 to the 5th power, which I know is 243. And in the bottom I'll have 2 to the 10th power, which is 1024. So those are the first 4 terms, but notice this term, the last one that was there, that's the term that I get when k is 5 in my sigma. So in terms of s, this would be referred to as s sub 5, and the remaining terms would be r sub 5. R sub 5 would start with 3 to the 6th plus 2 to the 12th, 3 to the 7th plus over 2 to the 14th, and so on. So that's what R5 would be, all the terms from here on. So if I do that in a calculator, my S sub 5 will be, can't see it, 1.538. And I also asked here if you would write down the formula for a sub k and think about what it's doing as k goes to infinity, because this is a source of confusion as well, that when we're trying to understand a series, there's really 2 different things going on. There's the, well, let me write this down first. The main thing here is that 2 to the 2k is the same as 4 to the k. And the second main thing is that when you have a power or something to the k over something to the k, that's the same as this. So this goes to 0. When you take a number between -1 and 1 and just raise it to a large power, it's going to 0. So that's worth checking. But notice the terms going to 0 is actually a requirement to have convergence, but it's not enough to know that to get convergence. And this is different from the series. The series is not going to 0. The terms that are being added up are going to 0, and the series is getting closer and closer to something else. Even just the first 5 terms, we already saw, the first 5 terms add up to more than 1.5. So there's no chance that we could say the series is going to converge to 0. But the terms do converge to 0. Those terms to be added. Then down here on the follow-up, we're supposed to use the actual geometric series formula, and so that would be the first term, which I have written down above, and then 1 over 1 minus the ratio, and you can see the ratio is 3/4. You can do that by either taking the ratio of consecutive terms or just looking at that final thing I was taking in the limit. The powers, the number, the base that's being raised to a power is the ratio. And then you get 9/16 times 1 over a 4th, which is 9/4. All right, so let's see one that's a different type of series. The ones on this page are all alternating series, which are also easy to work with in terms of understanding their convergence and also getting estimates for them, but we'll rarely be able to get an exact value for one of these series. So again, let's look at number 3. We're supposed to be doing the first 4 terms here, so I'll have negative 1 to the 0 over 0 factorial plus minus 1 to the 1 over 1 factorial plus minus 1 to the 2 over 2 factorial, and then plus minus 1 to the 3 over 3 factorial. And so that negative 1 to the k is just making my terms alternate adding and subtracting. Notice that the term I have here is the one that I got by putting 3 in, and so technically I would refer to this as s sub 3. And then the remaining terms are going to be 1 over 4 factorial minus 1 over 5 factorial, and so on. So this would be referred to as r sub 3. So you can add up those numbers. They're not very complicated because it's 1 minus 1 plus a half minus a sixth, so that just adds up to a third. It's pretty easy to do. The formula for the AKs here is just 1 over k factorial. Remember that when we do alternating series, we usually let the negative 1 to the k thing alternate, and then we refer to the numbers that are being added and subtracted alternatingly as our a sub k's. It's pretty harmless to keep the negative 1 to a power in there, but since we have to take a limit, we'd rather not have everything we can do to simplify it, the better. So keeping the negative 1 to the k is just going to make it harder to think about. So have limit as k goes to infinity of 1 over k factorial. This is a case where the denominator is definitely going to infinity like crazy, and the numerator is fixed. So this definitely goes to 0. In the follow-up, I'm being asked to try to give an estimate to these things. Remember the error bounds. The error bound for an alternating series is that, in this case, I want to know what's the biggest that r sub 3 could be. And the theorem says that r sub 3 is no more than a4. a4, remember, is right here. It's just the formula. So a sub 4 is just 1 over 4 factorial.
But not Donald Trump.
So a4 is 1 over 4 factorial, which is 1 over 24. And remember, another way to think about the error bound for an alternating series is just that your r sub 3 is bounded by its first term. So r sub 3 in absolute value is no more than 1/24. And if you don't remember what to do with the plus and minus signs, remember this should always be positive. So put absolute value bars around it if you need to, if you can't remember what the a's represent. But we want to measure error as a positive amount. All right, let's look at one more example. So the 1/3, I guess I should say the conclusion here. The 1/3 I got here is within 1 over 24 of the exact answer of the infinite sum. So the infinite sum is, so it's within 1/124th of 1/3. All right, one more kind of series. These are the hardest ones we have to work with because they're not alternating and they're not geometric, which means our only tool is to do some kind of comparison to an integral. So let me do number 4. This is the easiest kind. These are called p-series because it just has a k to a power p in the denominator, and nothing else is going on. So we can generalize what these do, but let's go ahead and try to do it. So first 4 terms, I'll have 8 over 2 to the 5th plus 8 over 3 to the 5th plus 8 over 4 to the 5th plus 8 over 5 to the 5th. So those are my s's. Notice that the last one I wrote there was 8 over 5 to the 5th, sorry. 8 over 5 to the 5th. In other words, it was when k was 5 was the biggest term I had there. So I'm going to refer to that as S5. And in this problem, S5 is, hang on, Looks like my S5 is 0.2933. The R terms, start writing these in blue. The R terms will be 8 over 6 to the fifth plus 8 over 7 to the fifth, and so on. And so in this case, what the theory tells us is that, so this will be referred to as R5. The theory says that R5 is no more than the integral from 5 to infinity of the continuous version of this function, this thing that R sigma is. So that's what the error bound is for things that can be integrated. Notice that these match, so it's easy to remember. And so as long as I can do the integral on the right-hand side there, then this actually ends up being useful. In this case, that's an easy integral because the thing I'm integrating there is x to the minus 5. So my power rule says to bump up the power by 1, divide by the new power. So I'll have as my antiderivative negative 2x to the minus 4. And then I'm plugging in 5 and infinity in there. So anyway, so that's pretty straightforward integration problem. So what I get when I do that is that this partial sum that I got, this number that I got from just adding up the terms up to 8 over 5 to the 5, is within, let's see what I get. I got 0.0032 as the value of this. So this series, I got 0.0032 as the value. So this estimate, that's an estimate for the entire infinite series, the entire thing going on forever. The S5 is my estimate, and I know that that is within 0.0032 of the exact value of the infinite sum.